Hello everyone. Thank you for joining our session today. We are going to talk about very interesting topics, so I'm very excited about that. My name is Yaron, and I'm Senior Engineering Manager. And here with me, Kevin McGee, a Principal Software Engineer. We are both from ElastiCache and AWS team. So a moment before I dive into the agenda of today, you are in the right room if you are interested in accelerating your application performance and lowering your scaling cost. You might be a software engineer, DevOps, or CTO, and you want the best to understand how to leverage the advanced data structures that ElastiCache can provide you while serving millions of requests per second, and all that with microseconds response time. So if that is true, you are in the right place. So what we're going to talk about today, I'm going to introduce you ElastiCache and Valky, and then we're going to explore together some advanced use cases, and we're going to finish with best practices and operational overview. So Amazon ElastiCache is a fully managed service that makes it easy to deploy, operate, and scale your in-memory data store on the cloud. It provides significant improvements of performance to your application by allowing microseconds response time. We today support three open source engines. First one is Redis open source. Second is Memcached. And last, that was announced this year, is Valky open source. I will speak a bit about it in the next few slides. We support multiple core of features. You can see that we support multi-AZ, 4.9 SLA. We had a lot of security aspect and compliance aspect. And we have a very good integration with other AWS services that makes it more easy to work on the cloud. Now, customers use a lot of and different use cases when they're using ElastiCache. So from the first glance, you will see that there is not much common between them, which is actually true. But thanks to the rich API and the data structure that Valky and Redis open source provide us, we are capable to provide all these use cases and to do that very effectively and fast. So let's talk about Valky. Valky, this year, Amazon ElastiCache and Memory and DB announced the support of the third open source called Valky. Valky is a high-performance key-value data store, and it's a community replacement for Redis. It's built by the existing Redis open source contributors, and it's a drop-in replacement for Redis open source 7.2. It's hosted by the Linux Foundation, which promises you that it will be open source and stay open source for good. Valky leads the way in terms of performance, reliability, and efficiency. We at the AWS team contribute to the open source community. Two major contributions. The first one is the performance aspect. We contribute the new threading model that unlock the 1 million requests per second. Now it's available also on the open source version. We also contribute the efficiency architecture that help to reduce up to 20% of the memory usage. Now, that's enough with the introduction. Let's start with the real fun things that we want to talk. And for that, I want to build with you together an example application. We're going to tie all the use cases to that application so that we're going to build together. So for that, let's imagine that you are a system architect, software engineer, or DevOps engineer, and you've just been hired to a new cool startup. As like every new startup, we have a small investment in the beginning, but still we want to choose and to build the infrastructure flexible and scalable enough so we can scale our infrastructure according to the incoming workloads and additional customers that will join our marketplace. So today we will follow the journey of this startup to learn how you might choose the use case, the right use case when you work with ElastiCache. I want to start first with a caching concept and to show you how you can improve your performance, but not only that, how you can reduce your infrastructure cost, and later we will see how we can go even more advanced on the caching side. So let's assume that our application is running on EC2 and we choose Amazon RDS to store the data persistently. Now we know that Amazon uses the disk to store the data, and there's some additional latency when we want to fetch the items from the disk itself. But up to some level of workloads, this can work perfectly, and as long as we add in more and more workloads, we have the option to scale up the RDS size. We can choose a bigger size of the instance that use RDS. We can also have the option to scale out, add more replicas, so we can scale the read throughput on the RDS. But at some point, we might reach to some upper bound, and we need to think how we can increase our infrastructure even more when the workloads kicks in. And for that, let's assume that we're going to use Amazon ElastiCache when it's explicitly stored the data on the memory. And memory is 20 times faster compared to the disk. Now, it's not that RDS does not have caching layer. It does have caching layer. It stores the block of the data, page of the data on the cache. But on some complicated SQL queries that require some, for example, join for multiple different tables, you might need to run across all these pages and to fetch some data from the disk, and this could cost us some additional latency. While in Amazon ElastiCache, we can store only the result set and fetch it directly from the cache and to achieve the microseconds response time. So once we populate the item into the cache, we can immediately start to read the data from the cache. And at that moment, we can improve our query response time and achieve the sub-millisecond latency and relieve some pressure from the backend. We can also optimize our cost by allowing the backend to scale down. Now, I want to review with you a few caching strategies, and let's choose together which one of them is most suitable to our marketplace startup. Let's start with the first one. It's called lazy loading. It's very simple. The idea goes like that. First, we're reading the data from the cache. If the item is on the cache, we are all good. Probably we finish the query by microseconds response time. If the item is not on the cache, we need to read it from the source. In our example, it's RDS. In that case, it depends on the complexity of the query. We might end up with between 1 to 10 plus milliseconds. Once we achieve the item, we can now update the item into the cache. So for the next time, it will be there when we need the item. The second approach is also simple, called write-through. We are first updating the item into the source, into the database. And right after that, we are updating the data into the cache. So we actually kindly duplicate the items on the source to be identical to the cache, and vice versa. So we go through across them. We have some cons and pros choosing each of them. But for our marketplace, I want to focus on how to combine these two and to create different strategy. And for that, I want to use the lazy loading for reading the data from the cache. And I'm going to use the write-through approach to update the item on the cache to be invalid when it requires to be invalid. So let's see how it works. First, we are reading the data from the cache. Then we're reading the data from the database itself. Now I'm choosing DynamoDB to do that. And right after that, I'm going to update the item on the cache. Now, let's assume that we are going to change this item or different item on the source itself, and we want to make sure that the item is not stale on the cache. So for that, I'm using DynamoDB. It's called the triggered feature that I'm going to trigger a Lambda function that asynchronously going to mark my cache as invalid and to delete this item from the cache. So as you can see, I'm combining these two approaches and create something that is very unique to our need. Now, in some of the cases, we want to recache hot items before they get expired. So to solve that, we can create a background task that updates the cache before the expiry happens. In this example, you can see that I'm using the multi-command. Multi-commands allow us to queue multiple different commands and to execute them all in once on the server side as one transaction and to keep the atomacy of the multiple commands. In this example, I'm first fetching the item from the cache. Then right after that, I'm checking the expiry using the TTL command. And once I'm executed on the caching, I'm receiving the value and the seconds before expiration. So in this example, you can see that how clients get slowly listening the expiry until the last client will cross the 5 seconds threshold. Right after that, it's going to prefetch the data from the database and to repopulate it into the source. Now, we might want to avoid also from a problem called tendering head problem. The tendering head problem occurs when multiple processes or threads attempt to proceed simultaneously, often resulting in high contention or resource strain and eventually causing to bottleneck. And this is something that we want to avoid. So let's assume that we have a very hot item on the cache that's going to be expired very soon. So what we're going to do, what will going to happen? All the clients going to connect to the cache to retrieve this hot item that already expired, and they will receive a cache miss on the same time. What's actually going to happen is that they're all going to refer to the RDS, put more pressure on the RDS, and eventually impact our latency and the performance. So we can build a synchronization mechanism like a barrier that allow only one client to make the request and to repopulate the item into the cache. So once this particular client, fetch the item from the source, all the other clients will wait until he finish. Once he finishes to fetch the data and to update it into the cache, then we can all the clients can read it from the cache as well and to enjoy from the cache it and the microseconds response time. Let's understand even more how you can implement that. And for that aspect, I'm going to show you only 2 clients. So let's see one by one how it actually works. The first client was a bit faster, and he tried to fetch the item from the cache, but the item is not on the cache anymore. He will receive a nil. Now the second client tried to fetch the same item. He will receive a nil as well because the item is not on the cache. The first client, as I mentioned, he was a bit faster. He's going to acquire a lock, and he will succeed. The lock defined on the cache itself. Right after that, he's going to query to refetch the item from the database. Now the second client tried to acquire the same lock, but it's going to fail because the lock is already acquired by the first client. So what he will do, he will wait, check periodically when the lock is going to be free. Once the first client finished to fetch the item from the database, he can update the item into the cache and free the lock, which eventually free the other client to wait and to retrieve the item from the cache. This is the way we create the synchronization using ElastiCache like a barrier and make sure that we're avoiding the tendering head problem. So I show you different examples of caching, specifically using RDS and ElastiCache. But it's important for you to know that we are not bounded only to RDS. We can also cache S3 objects because, and to improve the performance and to save cost because we don't need to do the I/O to the S3. We can directly go to ElastiCache. ElastiCache uses Valkey, and Valkey is a binary safe, and so you can serialize almost everything on Valkey and Redis open source. So everything that you can serialize, you can store the data as cache on ElastiCache and enjoy from high performance and reduce your cost. Let's see even more advanced use case of caching. It's called client-side caching. Usually, customers use it for even much more lower latency. Maybe it's sometimes because of the convenience of using the local cache on the application itself. So the idea is very simple. We are fetching the item from the cache. Once we receive the data, we store it on the local cache. And from that point, we don't need to talk with the remote cache anymore until the item is going to be stale. So how we define if the item is stale? We have 2 approaches. The first one is time to live, expiry. So once the item is, the expiry time is elapsed, the item is not valid anymore. The second approach is to subscribe to a channel. And once we get key update, we get the key notification, and we can mark this item as invalid. Valkey has two different approaches of implementing client-side caching, and specifically for invalidation. The default mode says that server going to remember all the mapping between the clients and the keys that they updated. And for that, he will be able to update only the specific client with the changes on his keys that he interested in. But the problem here is that we are consuming memory on the server side. The second approach is broadcast mode. Now the client is subscribed to a prefix, and once a key with the same prefix that matches the prefix is updated, then we will get a notification message. So let's dive even more and see how it's actually implemented. You can see here that I have a client application and a connection pool that we always recommend to use. The reason that we recommend to use connection pools is because TCP connection is computationally expensive operation compared to typical Valkey command. For example, handling set and get command is in order of magnitude faster if we are using an existing connection. So we're going to take our connection pool and to split it to two segments. The first one will be connection 0 we'll use as the invalidation connection. It will consolidate all the invalidation for all the other connection. And connection 1 to 9 we'll use as the data connection. All the data will go through DAT connections. So connection 0 will subscribe to the invalidate channel. And all the other connections will use the redirect tracking to connection 0. And every time that we'll update one of the keys, we will receive it on the invalidation message, and we can update the local caching. OK, so we understand how to improve the performance using caching and to reduce the cost. So now let's see why we need to use a session store for our marketplace. So for our marketplace, we need to store session for every connected client. And the idea is to include this, in the session the shopping cart, user preference, authentication, and other things that we think that it's important to use on the session. Our challenge is to have a low latency and high concurrency data store to process fast-moving ephemeral session data. And to be more concrete, we're going to use the session store to create personalization. So each of the clients will have a different look and feel when they are connecting to our website. So the clients connecting to the backend through the load balancer, which balance the connection across the backend server. So we can see that each microservice contains a list of user sessions, but eventually we store all the session on the ElastiCache, because here as distributed memory or distributed caching. So when a server is either removed or added, all the session remains valid on the distributed caching on ElastiCache, which provides us a seamless experience for our customers and allow us to run our microservice environment in a stateless model. It's very common to use a hash data structure to store the session data. So the way that we use hash data, we first have the hash key that is the identifier of the hash, and we have keys and values respectively that the ID is mapped to the value itself. And to build that, we can use the hset command with the ID of the hash, and then we can have a list of key value pair of the hash itself. Now, the hash is very flexible and allows us to enjoy from a constant time to achieve only a single value, to use the random access to achieve a single value from the hash. So in this example, we can use the hget command and to retrieve only the name of our object. Let's see how it works in the code. First, we are connecting to our ElastiCache server. Then to create the session, we use Python clients. So for that, we're going to use dictionary map, where we generating the hash data using key value. And we're going to generate the session ID. We're going to store the session ID on Valkey, and for that, we're going to use the hset command that we use the session ID and the dictionary that we just stored. And to retrieve the data, we're going to use the hgetAll command with the session ID that we just generated. Now, for that, we can now unmarshal the session ID to decode it to the internal session object that we have on our application. Okay, let's see how we can add some machine learning capabilities to our marketplace. And for that, to be more concrete, we're going to build machine learning-based recommendation for our users, so they can see what pictures we are recommending for them specifically. I'm not going to talk about the model itself, but I'm going to show you how ElastiCache can be integrated as part of the machine learning infrastructure. So for that, you need to understand what is feature store. Feature store is one of the most important pieces of the machine learning infrastructure. It provides a singular source of available feature for training and inferencing use cases. We have two types of feature store. The first one is offline, that training, model, and batch scoring. And the second one is for extremely fast feature calculation. In this diagram, you can see the architecture that we choose to build the machine learning infrastructure. And we use FEAST as the central processing system that we are used to register the feature definition, which can be later used for training and online inferencing. We're going to use Amazon RDS as the offline feature store and ElastiCache as the online feature store to serve features in ultra-fast response time for online inferencing and making real-time prediction using credit scoring model. To define it, it's very simple. We're going to use the feature store.yaml, and as you can see, I'm defining the Valkey as the engine for the online feature store, and we're providing the ElastiCache endpoint to access this feature store. And for offline feature store, we're going to use the Redshift. We're going to provide the admin credential, and that's it. Same as the feature store, same as the session store, we're going to use here also the hash data structure because of the random access, because of the flexibility. And the hash key will be the feature name. The hash value will be the feature value. That's it. Let's go now for the real-time analytics, and I want to call to Kevin to continue. Hope that you enjoyed the first part of the session.
Thank you, Yaron. So I want to talk through a couple of examples of how you can leverage ElastiCache and the Valkey API to power some real-time analytics use cases for our example application here. So the first question we want to answer with respect to our Night Sky marketplace is which of the photos are most viewed? And for that, we want to use something like a leaderboard. So in this example, we see 4 different images on our leaderboard, each of which has a score associated with it, which is the number of views that they have. And within the Valkey, we can represent this using the sorted set data structure. So what exactly is a sorted set? It's a combination internally within the Valkey engine of 2 different data structures that you will have learned about from your intro CS classes. The first is the hash, mapping what's called a user to a score. In this case, our users are the images that we're storing for the views, and the score itself is the number of views that it has had. But to maintain the sorted order, we need another data structure. And in this case, it's implemented using a skip list that maintains the sorted order by score. So you see the different pairs of images and view counts there from lowest score to highest score. What's interesting is that this skip list is doubly linked so that you can iterate it both forwards and backwards to get things in from highest to lowest or lowest to highest score. The combination of these 2 data structures allow you to do log-n operations for both reads and writes on the data structure. So let's see how you would actually use it in practice. So within the Valkey API, a lot of the commands are prefixed with a letter or set of letters that indicate what data structure it operates on. With leaderboards, with sorted sets, the Z prefix, the Z letter, means that it's operating on sorted set. So to add items to a sorted set, you use the zadd command. And here we're calling it a leaderboard views, and we're adding image 1 with 31. And as soon as we do that, it creates this sorted set with the skip list shown below of just one entry. And we can do that repeatedly for those 4 example entries we saw before. And every time we do it, it updates the data structure in real time so that it could be queried as we add new entries to it. So that's an example. It's not exactly what you'd want to do in the application itself, where you likely have these images already populated and you want to increment view counts as new views come in. And there's another command to do that, where you can do zanchor by, which will increment an existing value or a new value within the sorted set. So here, if I do a zanchor by image 1 with 10 views, then instead of going now at 31, it'll change to 41. And so it returns back the new updated value and then also adjusts the position within the sorted set. So there's a number of different ways that you can actually query this data structure. The one that we'll use here is leveraging the zrange command. And it has a variety of different options that you can use. We're here just going to display the entire leaderboard from the highest score to lowest score. So it has a set of bounds that you can provide. Here we're just doing from infinity to 0, so it's there's no bounds in terms of start or stop. And we're querying this sorted set by score rather than by the actual user or image ID here. And we're also doing it in reverse order using that doubly linked property I talked about earlier. So we're going from the tail to the head. So if we do this, we'll get back all of the key value pairs within our sorted set. So you see image 4 is the most viewed picture with 56 views, and then image 3 is the least viewed with 18. This allows you to do real-time analytics and update and read with microsecond latency within the Valky engine. So let's talk through another example of real-time analytics that you can implement using the Valky API, and that is unique users for each photo. So instead of just the total view count, you want to see of your user base how many unique views or even unique likes, their sentiment analysis there would be. So each user here is mapped to a given image in this example. So the naive way to do this, the most obvious one, is just to store all of these different user IDs in a set. So in this example, you'd have a set of 4 items. The downside of this approach is that the space complexity scales linearly with the number of users that have viewed it. So you have O of n at space, and there are various ways that you can try and compress this data, but it still is ultimately O of n in terms of space complexity, which for an in-memory data store, you would like to be able to save your space. And so the Valky engine implements a solution to this with a data structure called a hyperlog. And this is a probabilistic data structure that will give you approximate set cardinality. So you're trading off accuracy for size. The specific implementation here bounds the total size to 12 kilobytes. So no matter how many users you add into it, it will be maxed out at 12 kilobytes of memory, but it maintains a less than 1% error rate. So it might not be as exact as an exact set count, but in a lot of cases, this can work close enough and trade off those 2 dimensions. It also allows for constant time operations, so it's very fast to manipulate. So let's see it in action here. Just like the Z prefix was used for the sorted set commands, you can PF is the prefix for hyperlog commands here. So you can use the pfadd command to add a set of users to a given hyperlog. Here we're just calling it viewers image 1. And we'll get back either a 1 or 0 based on whether the data structure was modified, whether things were actually added to it. So we added 3 from empty. Now it tells us that we've added it. If we then use the pf count command, we can get an estimate of the number of unique viewers. In this case, we get back 3 because there's no error yet. And if we try and add a duplicate to it, we'll get back a 0 because the data structure was not updated, and pf count would still return the 3 from before. So let's see how this works at scale. And so I ran an experiment here to add 10,000 numbers to both a set and a hyperlog within the Valky engine. to compare both the accuracy and the size. So with the set itself, we get back 10,000, which is the exact number of elements we added. But the downside is that the memory usage here was close to 420 kilobytes. And of course, that will grow the more items that you add to it. With the hyperlog, on the other hand, if I do the PF count, I see it underestimates the value of the users by about 13 here, which is within the 1% error rate of the data structure. But if we were actually to look at the memory usage of it, we'll see it is just about that 12 kilobyte boundary that we saw before. So over 30 times less than the memory usage of the actual set. So this is a good way to both estimate unique viewers without using the large space that a set can grow to with a large number of users. So let's move on from real-time analytics to talk about some of the geospatial capabilities of the Valky engine and how you can leverage that in this example application. So let's say we want to answer questions and be able to display to users in our marketplace what night sky photos were taken near them from their given location. So in this case, we have a map here of Las Vegas and us roughly on the Las Vegas Strip. And what you can do in Valky is to take that latitude and longitude and use something called the geohash algorithm. So with a given latitude and longitude, we can encode it into a 52-bit integer. And that integer can then be used in combination with that sorted set data structure that we saw earlier to leverage it as a score. And then this allows for things like bounding box and radius querying on top of the sorted set. So it becomes its own data structure, a geoset. And just like the sorted set, it allows for log n operations in terms of adding or querying the set. So let's give some examples of how you would do this. Let's say you have two images taken, one up here by the Strip and one down by the Las Vegas airport. We can use the geoadd command to add the latitude-longitude pairs for each of those images into our geoset and get back a 1 saying that they've been stored. Let's say that I'm trying to access this website over here from Treasure Island and trying to query which things were close to me. With that, I can use the georadius command. And so I can feed in my latitude and longitude to the command and give a bound for it. So in this case, 5-kilometer radius. And with that, both of those images are within 5 kilometers, and so I can get both of them back here. Optionally, I could add more parameters to get back exactly how far they are from me, but here we're just showing the simple version. And let's say I want to do a smaller bound here, so I want to do a 1-kilometer bound, even to make it more tight. With that, I just get back image 3. So in addition to doing radius-based commands, you can determine the distance of objects within the geoset. So let's say we want to see the different, how far away image 3 and image 2 are from each other. With that, I can use geodist and pass in just the references, the object ID is image 2 and image 3, and get back that result here in meters. And it'll tell me that they're about 4.5 kilometers from each other. So there's a variety of powerful commands that you can use to query different geospatial data within Valky. I want to walk through another example of how you can leverage it for rate limiting. So the concept of a rate limiter is fairly simple, where let's say you have a distributed application and you want to be able to limit the downstream calls to any resource. In this case, let's say we have a weather forecast functionality in our night sky marketplace, and we want to be able to limit the downstream calls to it on a per user basis. We could do it on each of our applications, but in a distributed application, then there's no way to synchronize the rate limiting functionality between them. And so for that, we can use Amazon ElastiCache, sort of like we saw for the session store use case of being able to have them all synchronized on the back end. So we'll walk through a simple and then a more advanced use case for rate limiting. The simple one leverages the simple string data type that we saw before but uses it for numeric operations. So in addition to doing sets and gets on binary safe data, you can actually manipulate a string as a number in an O of 1 time. So let's say I use this anchor command on my key, which I'm calling number. If it doesn't exist, it'll increment it by 1. It'll create this key called with a value of 1. And then I can continue to call increment on it, and it'll increase the value each time and return to me that new value. So we can use this capability to build a pretty simple rate limiter. We'll also leverage something called Lua scripting, which is another capability that Valkey supports. So Lua scripting is a scripting language, and you can actually run scripts on a Valkey server within ElastiCache that allows for atomic operations, sort of like the multi-exec case we saw before that Yaron talked about, but allows you to do more complex logic on the server side. So what we want to do is our general rate limiting algorithm is to start our counter at 0, empty. We'll count up to a predefined limit, in this case 3. And then we'll use basically the TTL value to delete the item. And we'll deny more requests until the TTL is expired, at which point the counter will reset, and we'll continue to be able to make calls at that point. So in a general animation sense, we see requests being made. The first time the request is made, the TTL gets set off. As soon as we've made 3, no more requests are allowed until it gets reset. And then we can make further requests, which will then reset the TTL again. So what does the script look like to actually build this? We'll walk through it, as it's fairly simple, can fit on one screen in this time. First, we set our limits here, which are just hard-coded, which in this case will be able to make 4 calls in a 10-second time period. We can take in an argument to our script, so we'll take in a per-user key, and we'll then get that key, or if it doesn't exist, we'll start out with the default value of 0. If it's 0, we have to actually set it to be able to kick in the expire time. So we'll set the current value of 0 and allow the TTL to start working. And then we will, if we're below our limit, we'll call increment and return 1, saying that the call is authorized. And if we're above the limit or reached the limit already, then we basically return 0. And successive calls will continue to return 0 and do nothing until a background process within Valkey reaps that key, and then the process can reset basically from empty. So that works as so let's talk about how to actually invoke this script within the Valkey API. For that, we have 2 parts. We have to first load the script and then invoke it. So to actually load the script, you can use the script load functionality and then pass in that entire script as an argument, as a string argument here. And we'll get back a SHA-ID, which is a unique identifier of the script itself. We can then use this identifier within the client to evaluate the script. So we do a val SHA with the script ID and can pass it those arguments we talked about before. In this case, just a single argument, which is the key that we're operating on. And various frameworks and clients will abstract this in different ways so that you don't actually have to manipulate the SHAs directly, but this is the general process that you would use to invoke scripts. So let's look, and in this case, we get back a 1 saying that the first call is authorized. So let's look at a slightly more advanced version of rate limiting, which is with a token bucket algorithm, which some of you may be more familiar with. In this case, we have a fixed capacity bucket where tokens are added or refilled at a specific rate, and then requests will actually consume those tokens and remove them from the bucket. So in this example, we still have user-specific buckets, but we have more variables here. We have both capacity, we have refill rate, and current number of tokens. And so instead of a simple counter, we'll use a hash data structure to store all of the information associated with the specific token bucket. So in this case, we have to maintain the current number of tokens, and then the last update time in milliseconds since epoch, which we can use each time a call is made to determine how many tokens to refill on the bucket. So let's walk through what that script actually looks like in a couple different parts. So we'll start out, rather than hard coding our variables as we saw before, we'll take them in as arguments to the script. So we'll be able to get those passed in on from the client, as well as our key. We'll then retrieve all of that metadata from the data store using HMGet, and also get the current time, which is a function of Valkey. We then have to go through the function to refill the bucket. So if it already exists, we'll calculate the number of tokens to add to the bucket based on the difference of the last refill time and our current time. And we'll cap it to bucket size if we have more than that. Otherwise, it's the first time that we've made the call, then we start out with the bucket size tokens. Then we'll determine if the call is allowed. So in this case, rather than counting up, we'll count down. So if we have at least one token, then we will allow the call and subtract it. We'll then update our state using hset to update both the last update time as well as the current tokens. And at the end, we're still using an expiry here, not because of correctness like we were using it for in the simple algorithm where we were requiring it to be expired to maintain continuing calls, but here it's just a memory optimization because after if you haven't called for a while, we want to reap that state and it can start over again from scratch. So it's a memory optimization technique, and we'll still return the allowed value. Now I want to spend some time on the best practices and operational overview of working with ElastiCache and Valkey to give some tips and tricks when implementing these advanced data structures. So the first thing to remember is that caches are not persistent. They're not a replacement for a database. So when you're looking at ElastiCache, it's best to use it for ephemeral data. And what I mean by that is that although we have a 4.9's availability SLA on multi-AZ caches, the system will prioritize availability, that is being able to continue to accept reads and writes, over the consistency of the data. So what this means for how it's implemented is that replication between a primary and a replica is asynchronous. So a single node failure of a primary can cause tail-end data loss in the system. So if you have a user that's writing to a replicated setup with a primary and a replica, they could set a key on the primary and get back an OK, but asynchronously that primary will send the result to the replica. So if that fails, if the primary were to fail before that happens, then that data is lost even though it's acknowledged on the client side. So there's a couple different ways to handle that. The best practice is to basically plan for this loss of data and be able to accommodate it. One way is just to tolerate loss, which for a simple cache you can do just by repopulating from the database in the event that that item's missed, or for something like a rate limiter, maybe it's okay to miss a single update and just make one extra call when failure happens. But for something more complex, it may require you building some way to detect the loss and rebuild or repair it. For example, if you're not able to tolerate loss of data in a cache, then rehydrating asynchronously can be more complex. And for these use cases, if it becomes more of a burden than it's worth, then I would encourage you to consider Amazon MemoryDB, which is another AWS service that my team supports that offers a Valkey compatible API, but the difference is that it is durable and consistent. So it uses a multi-AZ transaction log behind the scenes in order to ensure durability. In terms of how to remove items and keep a stable size in the cache, there's a variety of different ways to ensure the data size remains below a certain threshold. The first is with explicit deletes or overwrites as a way to, of course, manage data set size. The other is with time to live, which we covered briefly. I'll go into a little bit more detail. And the last is eviction. So let's dive a little bit more into the TTL options you have. So it's the most common way that our customers manage their cache size by setting time to live, which automatically causes items to expire. TTLs in Valkey are explicitly assigned to an item. So there's no global or default TTL. You have to do it on an individual per item basis. And you can set it either relatively with the expire command or with a fixed time using an expire at command. One best practice when working with TTLs is to add a random jitter to it. What you want to try to avoid is that a number of different items all expire at the same time. because it can cause a thundering herd problem like Yaron talked about earlier, except it's harder to manage that because it's across a variety of different keys as opposed to on a single key, where the strategy we showed earlier can help leverage. So to avoid this, adding some jitter to have large expirations happen over time can cause fewer problems. Let's talk a little bit about eviction. So eviction is a way that you can automatically remove items from your cache when memory is full, when a storage size has been reached, basically. So there's two different eviction pools that you can have based off of your eviction policy. You can either evict items from the set of all items in the server, or volatile items, which is those that are set with a TTL. And in most cases, those that are set with a TTL are more okay to remove perhaps before the TTL has been invoked. And so it would be the first choice for things to remove on eviction. And within those, there's three different algorithms you can use. There's least recently used, which removes things that are least recently used. There's least frequently used, where it keeps track of how the frequency, the number of calls to a given item. Or there's just based off of the expire time itself, which you can use to order evictions. So one of the common questions we get when customers come to us is, how should I size my cache? What should I think about in terms of putting it in front of a database? And the answer is that there's really a one-size-fits-all answer to this question, because it depends a lot on your use case. And it's really an iterative process to find which cache size works the best for any given application. In general, there's a trade-off between the cost, basically the size that you've had, and the cache hit rate. So for pure caching workloads, you're going to get diminishing returns after a certain threshold as you continue to scale out, where it might be better just to keep a smaller size and have perhaps slightly lower hit rate overall. But for ones where you're using it more persistently, like for the sorted set leaderboard example we saw before, then it's really dependent on the number of images you have in your database, and that is harder to optimize on. So it depends on how you're actually leveraging it and how many different combinations of workloads you're putting on a single data store. In general, one best practice here is to leverage auto-scaling, which can kind of figure out some of this for you. So we have two different modes within ElastiCache. One is ElastiCache serverless, which can then auto-scale under the hood. You don't have to do anything for it. And you're charged only for the data set storage size that you store at any given point in time, as well as the requests that you make. So it's completely serverless. It does allow you to set cost control bounds. So say I don't really want to store more than this number of gigabytes of data. You're able to do that, and eviction will start kicking in at that time period once it's scaled up to that size. With the node-based installation of ElastiCache, you can leverage application auto-scaling, which allows you to set different triggers based on metrics that we publish. So things like CPU utilization or data storage size, and you can automatically scale out or up based off of response to that. So just a few usage best practices before we end and open it up to questions. So as Yaron talked about before, one thing we want to emphasize is that though you get microsecond response times, one common pitfall is to do repeated connections to the cache. And the connection handshake itself can be relatively expensive. It involves TCP handshake, perhaps TLS and auth. And so using long-lived connections, either through a connection pool or otherwise sharing connections across invocations of the application, will give you the best performance overall. Reading from replicas is another way to both improve throughput and latency. So with any primary, you can have up to 5 replicas within ElastiCache, and you could use it to not only scale throughput, which will scale then linearly across all of those nodes, but you can get better latency because you can go to a node that's in your specific availability zone. So the primary might be located in a different availability zone. Replicas can be within the same one, and that can cut off perhaps a millisecond at most of between with your calls. Another thing, as I've talked about, is to understand the computational complexity of any command that you're operating on. So things like key star is linear with the number of keys in the data store, which can become quite large. The things we talked about before, log n, can still scale relative to the number of items within a given set or list or hash, for instance. And so in addition to that, limiting large multi-gigabyte objects is another best practice. So for example, if you had millions of items in your leaderboard for sorted set, then perhaps it would be better to split it up across multiple sorted sets to be able to make more efficient use of multiple servers, as well as to minimize some of the synchronization overhead between those items. And with that, I'd like to thank you for coming out.